two more examples. Example 5, find this limit. Here we will use this one. This limit shows when h is small, I mean the absolute value of h is small, then the sign h almost h, because the ratio of sign of h and h is 1. So when x goes to 0, then this number almost 7x over 4x will be 7 over 4. Yes, but how to give a reasonable process? So here we treat this one as a composite function of 7x and the sine. Or more precisely, if we put theta to be 7x, then theta is a continuous function of x. And the x approaches 0 implies this one approaches 0. Conversely, x is also a function of theta. This is also a polynomial of theta. When theta approaches 0, x also approaches 0. So we can express this limit by in terms of theta. Okay, so by using of this one, in fact, if you are not, if this is fill the blank, right, blank, then you can ignore this one and write the 7/4 directly. But if you are required to give the solution, a complete solution, you had better write down like this. Okay, similarly for this one, because cotangent x is cosine x over sine x. We write this as these two expressions are the same, because if you multiply x, then x and x are cancelled, and x here. Because cosine is continuous everywhere, and cosine 0 equals 1, and this limit as x approaches 0 is also 1. This limit is 1. So these two examples use that limit. Okay. This is the section 2.6. The next section is entitled the chain rule. So far, we Uh, we know the definition of the derivative, and we also know some differentiation rules. Sum rule, difference rule, product rule, quotient rule, and also power rule. And today we proved trigonometric functions, differentiation formulas for trigonometric functions. Next, we will consider the differentiation formula for composite function. Composite function. Composition of functions. Suppose we have a function g a number x is mapped by this function g to this number g of x. Suppose this number is in the domain of another function f, then this number can be mapped by f again to f of u or f of g of x. In this case, when x is given and the g of x is in the domain of the function f, this number is completely determined by these two functions, and we call this number f circle g, the composition of these two functions, f and g. Okay, this f circle g is not f product g. Product means multiplication, but this is composition. Okay. Suppose f the function g is differentiable at this number. For example, x is the number 1. G of x is 10. And f of g of x is 100, suppose. For convenience sake. 1, 10, 100. Suppose g is differentiable at the number 1 and the g prime of x, for example, equals 2. And suppose f is differentiable at the number 10 equals 3. G prime x equals 2 means here, x is 1. G prime x is 2 means the slope here is 2. If we consider the increment of x is very small, yes, the concept of differentiability, differentiable of a function, a some number means locally it's linear. So if this increment is very small, then the increment of g is almost 2 times of this one. So if we write this as delta x, this is small, g prime x is 2, means delta u is 2 times of delta x. 1, 2. Okay. Again, if f is differentiable at g of x means, suppose this is 10, then if delta u is not so large, maybe very small, then the corresponding delta y will be 3 times of this one. 3 times. 1, 2, 3. So this is delta y. Differentiability means locally linear. The rate of change is 2, means this one is 2 times that one. The rate of change, this is u. Or this one. It's 3, means the rate of change is 3, means this one is 3 times of this one. Therefore, this one is 3 times 2, 6 times of that one. Therefore, we have f circle g, the composite function. The rate of change at the number 1 equals 3 times 2. 3 means the derivative of this one. 2 means the derivative of this one. At where? At x. At where? At g of x. At 1, at 10. Okay. This is the chain rule. So the chain rule is the differentiation rule for composite function. The complete statement of chain rule is given by here. Chain rule. Suppose a function locus g is differentiable at some number x, and suppose function f is differentiable at the number g of x. Then the composite of f at g is also differentiable at x, and the derivative of the composite function is the product of these two derivatives at g of x and x respective. So you have learned this when you were in the elementary school. 3 times 2 equals 6. But now, for nonlinear function, if it is differentiable, then locally linear. So this is exactly 3 times of this, 2 times of this one. And this is 3 times of this one. Therefore, this one is enlarged 2 times, then enlarged 3 times, total 6 times. Okay. Chain rule. How to apply this theorem? Don't think too much. Though we have a prime here, in fact, when x is given, this is a number, this is also a number, stands for the rate of change, 2 times, or times 2. And when x is given, g of x is also a number, this is a rate of change. In that case, this is 3. 3 times, or 6 times 3. So, this one is the product with 2 numbers. This is chain rule, just like multiplication. 2 times 3, 3 times 2 equals 6. 3 times 4 equals 8. 3 times 9 equals 18. So, in order to apply this one, you have to recognize a given expression is a composition of 2 functions. This first, then this one, whose derivative can be differentiate this first. For convenience sake, differentiate this first at